I said I would talk about circuits a little bit. I'm going to range a little wider than that probably and try to cover topics from the whole course both today and on Thursday. So I find a problem with a whole bunch of resistors in the text. The problem says in that circuit, all the resistors they're rated at a maximum power of 1.8 watts. So maybe I will just remind you here that power, well, it's energy per unit time. Voltage is energy per charge. So I have energy per charge. That gives me some measure of energy. But if I want energy per unit time in some circuit element, then I need the voltage difference across it. So that's how much energy per charge I put in, or energy per charge I took out. And then the current through it, because that's charge per unit time. So if I have the energy per charge, the voltage times the amount of charge per unit time, then I have the energy per unit time either that I'm putting in, possible, or that I'm taking out of the circuit. The voltage drop across a resistor, of course, depends on, I'm going to put the minus sign in there just because the sign of the voltage drop, just because I tend to write it that way, the voltage drops in the direction of the current. Because the voltage drops, the resistor is taking electrical energy out of the circuit. But I just write that because you can put delta V in here and find out that for resistors, delta V is IR times I. So the power coming out of a resistor, coming out of the electrical system due to a resistor, this is power going into thermal energy. Energy is still conserved, so if you take energy out of the electron system, then you put it somewhere else. And that somewhere else is thermal energy, just the atoms bouncing around in the resistor. If I just put in delta V equals IR, then I find that that's I squared R. For me, that's the most useful way to think about the power in a resistor, is that it depends on the resistance, and it depends on the current in a big way. It depends on the square of the current. But you could also substitute for the I. You could have the delta V, and then substitute for the I delta V over R. And this is certainly just as good a way of talking, or just as correct a way of talking about the power dissipated in a resistor. It's for my uses, it just doesn't seem as useful to talk about delta R, because I mean delta V, because I can't, for whatever reason, I have an easier time thinking of the current than of the voltage drop across a resistor. So I like I squared R. But anyway, you can do either of the two. And in this particular one, I squared R might be the best way to deal with it. So you have the issue is there's this complicated circuit. And you know how to solve complicated circuits. You start writing down Kirchhoff's laws. This circuit is a mess. This is going to take you a long time writing down Kirchhoff's laws or writing equivalent resistances, which is probably the way you would do this one. You could say that this 20 ohm and that 20 ohm are in parallel with each other, and so you can replace them with a 10 ohm, it turns out. That 10 ohm that you replace it with is in series with this one, so you could replace that whole business right here with a with a 20 ohm resistor, the sum of those two. You can add those two together, then you end up with more things in parallel. These two are in parallel, you could replace them. There's a lot of calculations to do here. On the other hand, if you look at the circuit and think about the circuit, you will figure out where the problem lies, I think. And so sitting and looking at what you have to deal with is sometimes a quicker way to get to the answer than just chugging through calculations. You're still going to have to calculate things, but it might be easier to, ahead of time, to think about what you need to focus on. And so my question for you, the point is to find the maximum EMF, the maximum battery size where you don't burn up the resistors. So my question for you, what resistor is the problem? Which is the one that dissipates the most power? Okay, so the main answer is that the 40 ohm resistor has the biggest energy dissipated. So this is a question of I, the current squared, times R. So the first thing you might look is which have the biggest current. They're not necessarily going to have the biggest power dissipated, but that's a place to start. And if you look at which of them have the biggest current, I hope that you would really pin that down really quickly to this 40, that 30, and that 25 all have the largest current. They all have equal current, in fact, and the largest current. And so from that set, you would say the 41. But what happens if you go farther? What about, okay, these up here are all going to have smaller currents, and they're all smaller resistances, so they can't possibly dissipate as much power as the 40-watt one. So the only other ones are these, the 50 and that 50. Bigger resistance. So the current better be smaller if it's not going to dissipate as much power. It's only 25% larger resistance here. And you can see that the current that goes through there gets split because these two are equal resistance. It turns out it gets split equally. And so it's half the current through here, even though the resistance is 25% bigger. So the end result is those of you who picked B, the 40 ohm resistor, are right, that's the one that's going to dissipate the most energy. It's going to get the hottest first. In thinking about, in doing that, you automatically, now that you know that that's the biggest power drain, or sorry, the resistor the single resistor that has the most power dissipated, you automatically know something. You know that that's the linchpin there. That's the one that you have to worry about. You know that 1.8 watts is what it'll take, and since the power is 1.8 watts, and where are we here? The power is 1.8 watts. The resistance is 40 ohms. That tells you what the current in that circuit can be right away, the maximum current. Yeah.
What are the subscripts for the piece?
Oh, sorry. I meant to say these are for resistors. This is the general description for power that's always true. But for a resistor, delta V is minus IR, and so I know delta V, and so I can plug in either for delta V, that IR, or I can plug in for I, delta V over R. So these P's, these powers here, are just for resistors. So you can find the current right away, the maximum current through this 40 ohm resistor, and that's the current in this circuit. So the maximum EMF is going to be the EMF that gives you the maximum current, and you know the maximum current now. And so you still have to reduce all of these. You still have to find an equivalent resistance here. You still have to do are equivalent. In other words, you have to put these two in parallel together, and that gives you there something here in series with that, and then those three are in parallel, so there's an equivalent resistor there, and these two are in parallel, so there's an equivalent resistor there. Turns out it's 25 ohms. Then you have 1, 2, 3, 4, 5 in series at the end, which you can just add together and give you one big equivalent resistance, and the current you can get from E over R. So delta V around the loop is E minus IR, is 0. So if you look at the circuit ahead of time and try to figure out what's going on, think about the problem a little bit, you can get a lot of the way without doing calculations, or you can figure out which calculations you need to do it in what order. Because this looks horrible. It's not a lot of fun, but it's not as horrible as it seems. You don't have to calculate the power for every single resistor. In fact, you only have to calculate. You know that you look at this, you identify one of them, that's the maximum power, that automatically gives you the current, and from then on, I hope that you can deal with that problem. So this was just to say, thinking about a problem is a good thing to do at the beginning. You can save 10 or 15 minutes of algebra sometimes if you think about the problem for, how long did you think? I gave you a minute and a half. I gave you a minute and a half to think about the problem. That probably saved 10 minutes of algebra. Any questions about that one? Yeah.
So for the equation where it's E resistor is equal to I squared R or delta V squared over R,
Yes.
would you use R as R equivalent or R as the 40 resistor?
Well, the power equation there is for any circuit element that you choose. So I squared through this 40 ohm resistor times the voltage drop across that 40 ohm resistor, times the resistance. I squared through the 40 ohm resistor times the resistance of that resistor tells you the power dissipated in that resistor. The total current actually happens to be the current through the 40 ohm resistor also. But the total current squared times R equivalent tells you the total power for all of these looped together. But any one of them, the current through this 25 ohm resistance squared times 25 ohms gives you the power dissipated in that one. In fact, the current through this battery times the battery voltage, so current through the battery times the battery voltage, tells you the power that's being input by that battery. So this equation works for any circuit element, any individual circuit element, or an equivalent circuit element. And these resistor ones work for any resistors or any equivalent resistors that you want.